Hi, I'm Rajagopal from the Stanford Sustainable Systems Lab. Today I want to talk to you about one of our projects, Visualization and Insight for Demand Operations and Management, or VISDOM, a tool to model consumer behavior for electricity systems. Harnessing demand flexibility is one of the challenges we will have for future electricity systems. Consumers have flexibility of different types. For example, you'll have consumers that have smart thermostats that can be controlled both to pre-cool a home or in different on-off settings according to their presence or absence in the home. You can have electric vehicles, storage, or even flexibility in the form of changing behavior. Traditionally, flexibility has been extracted utilizing programs organized by an electric utility. These programs enroll consumers who derive benefits from participating in the program and, in exchange, contribute a bit of their flexibility. Some examples of programs are demand response program, for example, where you would receive a smart thermostat from the utility in exchange for letting them control your thermostat for 3 or 4 days of the summer. Another example of program is a time of use pricing program where consumers will have time varying prices during the day and in additional a critical peak pricing during particular days in the summer in exchange for, on average, a lower total consumption charge. And finally, you may even have rates and incentive programs of different types in order to adopt energy efficiency measures for your home. Program management includes, first, identifying the potential for a new program. Second, measuring the impact and performance of the program. And third, optimizing the deployment of the program across a set of consumers. Why is program management challenging? Here, I'm showing you a diagram that shows the distribution of consumers and their benefits of participating in the program. So the benefit is right here on the x-axis, and how many consumers obtain that particular benefit is in the y-axis. And traditionally, we see 4 classes of consumers. The first one are clearly consumers that when they are enrolled in the program, they achieve substantial savings. So those consumers normally enroll. So that's indicated right there. Second, consumers who when they enroll in the program, they may have negative benefits. So they're worse off or the electricity is more expensive for them under that program. So they are typically and traditionally not enrolling. But the majority of the consumers fall into these 2 classes, A and B. First, the class of consumers that have small positive benefits. Typically, they fail to enroll in the program because their benefits are small and they don't realize they may have that benefit. And second, consumers that have small negative benefits, but whom could start enjoying positive benefits if they did small changes to their behavior and habits. Okay. The performance of a program is measured by the yield. When we design a program, we have a certain amount of kilowatt hours of flexibility that are desired, and we then observe after the program is deployed what is the actual obtained kilowatt hours of flexibility. The ratio between the two in percentage is the yield. Traditional utility programs today enjoy yields between 10 and 20%. This is quite low, and this is why program management is hard. So why is the yield low? Today, the way programs are managed starts by identifying a small number of consumers for testing a program, sending them a questionnaire that allows you to collect demographic and choice information from these consumers, enrolling them in the program, and then observing their consumption before and after participation in the program. Based on that result and the demographic and marketing variables collected from the consumer, different type of predictive models are built to predict program performance. It turns out that these models don't perform as well because the stated preferences of a consumer are actually different than his actual behavior, particularly in something like electricity that does not have a huge impact financially to the consumer. Instead, we are proposing a different approach. We start with the whole consumer base, potentially, let's say 1 million consumers. We actually have a new source of data, smart meters, and they observe the consumption hour by hour throughout several years for every consumer of a particular utility. From this information, we can extract features that actually reveal something about the behavior of the consumer. It's something like an MRI. If I know that you have a certain pattern of consumption in the morning, I can likely guess that you were having breakfast. If I know that you have a certain pattern of consumption for a base load, I know potentially how much cooling energy you're consuming in your home. These features then can be used alongside the more traditional demographic and marketing information in order to build demand analytics and optimization methods and models. Moreover, now we can actually interact with these consumers in real time using web or apps and actually perform online learning. So VISDOM, or Visualization and Insight System for Demand Operations and Management, is a platform created to support this concept. It consists of 2 parts. First, a set of libraries that allow you to connect to your smart meter data, extract various features from the data. These features come from our own research, from traditional methods utilized in building science, and ideas from machine learning, for example. We have methodologies to utilize these features and then target consumers correctly, segment them according to their behavior, build response models that allows you to predict the savings or the consumption changes in a consumer under different programs, perform measurement and verification studies, forecasting, and even pricing. These libraries are built in Python and R and can be used in different ways to configure your own program analysis. In addition to that, we have built a web interface that allows you to browse through data from millions of consumers in different ways, through map or through distributions or comparative plots. And this allows an exploration of your consumer base with respect to the various features that we have. This project has been supported by various organizations like PG&E, ARPA-e, who funded the project, State Grid Corporation as well has funded us, AutoGrid, who has adopted some components, as well as OhmConnect, the SLAC National Laboratory, and the Berkeley National Labs. These organizations are either utilizing VISDOM today, or they have utilized parts of VISDOM into their own products and ideas. Let me give you an example of how VISDOM works. I'm going to utilize data from the Bay Area, from particularly 2 regions, a coastal region, San Francisco, and a more inland, warmer region, Bakersfield. The data consists of smart meter and automatically downloaded information from VISDOM on the temperature for each one of the zip codes where these homes are located, and the locational marginal price of electricity in these locations as well. Okay. And we have about 500,000 residential and business customers and 2+ years of data. So first, let's look at a very basic feature, the load shape that a house consumes in a given day. So traditionally, in utility planning exercises, in electricity planning exercises, homes are considered to follow a dual peak load shape, like this one right there. We utilized clustering methods and uncovered 200 different load shapes that explain 66 million consumer days. That is very interesting. You have load shapes that are dual peak, as you can see here, different forms of dual peak. But you also have load shapes like this one, where all of the consumption is happening at night, or this one where only in the early night you have some consumption, and so on. The more interesting aspect, besides the fact that 200 load shapes can explain all these consumer days, is that only 14% of our load shapes turned out to be the dual peak. The next thing we can do is, on top of this basic feature, which we call the load shape, the normalized daily consumption, we can build another feature, entropy. Entropy roughly measures how many load shapes a consumer utilizes during the year. You take the log of that number, and you're going to obtain a number here, a positive number that ranges from 0 to something large. So for example, if your entropy is 0, it means you consumed a single load shape for the whole year. If your entropy is 1, you consume 2, and so on and so forth. We can see that our entropies range from 0 to 6, so that is 1 to 32 load shapes are consumed in a given year. And here we have done a scatter plot of consumers and grouped them according to the total kilowatt hour of their consumption and the entropy. Right here in this lower left corner, we have consumers that consistently consume the same load shape but have a low amount of consumption. Here, they are very stable, consuming very few load shapes, but they have a high amount of consumption. And likewise, we can go to the other extreme, and we have a lot of different load shapes and light or heavy consumption. For example, a hypothesis is that a consumer that is consistently consuming the same load shape, much like a German or Swiss person would be very organized and consistent, might be more prone to maintain a behavior that he changes in response to a program, versus a person that consumes a lot of different load shapes and has a lot of variability in those load shapes, may be more easily adaptable in his behavior, but may have more difficulty in persisting on that change. So these features could potentially drive how you respond to programs. We also performed a similar analysis for small and medium businesses, and we found that load shapes are very distinct depending on the type of business, going from construction, manufacturing, retail, and food services. And you can see here, in retail, these are business hours. So for a retail store that's open late night, and this is a more traditional business. And for construction, you notice that a lot of work is done during the night, for example. A second ability that VISDOM has is now to actually measure savings from programs that are currently running. So there's two traditional ways to measure savings. The first one is the causal experimental design. In this type of program savings measurement exercise, consumers are randomly assigned into treatment and control groups, and the average consumption of the treatment group minus the average consumption of the control group is a measure of the impact of the program. So the difference between those two. An alternative that is also utilized in electricity is the non-experimental design. In this case, for every consumer that's in the program, we use his historical data to predict his future consumption. Based on that prediction, we assume our prediction actually tells us what the consumer would do in the absence of the program. The difference between his actual consumption and the prediction is an estimate of the savings of the individual consumer. So these are the two basic methods. Let's see some examples of how to do this using VISDOM. So we utilized VISDOM and we evaluated a causal experiment that was conducted for a critical peak pricing program. We were able to find that the savings in the bill, the changes and savings in the bill for a given consumer once he enrolled in critical peak program were actually quite sensitive to various features that we derived using our VISDOM methodology. The basic treatment effect is that they reduce, by just enrolling into the program, they reduce about 60 cents of a dollar every day. Additionally, if there are consumers who have a mean fraction of consumption in peak hours that is very high, so that is above 50%, they are in addition able to reduce $1.40. So they significantly change their behavior because those time of use prices and critical peak prices affect them much more since they have this high fraction of peak load shapes. So this is a feature from VISDOM. In addition, if they have low variance, meaning they're very consistent in their consumption throughout the year, they're able to reduce an additional $1.40. So we can see using this model that features are very good predictors of how consumers will save. We also studied for the second type of methodology, really how good and accurate are different types of baseline. What we found is that the performance of your method really depends on the size of the load you're predicting. So if I'm predicting loads for single homes, errors are typically around 50%. And this is across many different methods and so on. And there is a range here. Some homes are better than others. But now if I'm predicting for small buildings and commercial buildings as well, then my error goes down all the way to 10%. And if I'm predicting for the whole feeder, my error is 1%. So when we are baselining loads, we can expect large errors, particularly if you're looking at residential consumers. We utilized the baselining methodology to evaluate the performance of a consumer engagement program, demand response program by a company. And the program consisted of sending demand response signals to turn off resources that the consumer enrolled in his home in response to changes in prices or things like that. Particularly in this case, there are consumers that actually enroll appliances, and there are consumers that only promise to go and manually turn off something when they receive this signal. And for this particular program, we saw some very interesting numbers. We analyzed a set of about thousands of consumers, and we plotted the savings that they enjoy for each one when they receive the signal on average. And we found a few things. First, there are some consumers that actually reduce their consumption in response to the signal, which is actually what you want. But there are also some that actually increase, meaning potentially they're not even responding to your signal. Okay. If we consider those consumers that actually reduce, so if you are able to identify and only signal those that actually reduce, Then there's a second interesting phenomenon. In this plot, I have the cumulative savings of all consumers put on an axis between 0 and 100%, and here I have 0 to 100% customers. And what we see is that 35% of the customers are responsible for 90% of the savings. So if we are able to target consumers correctly by predicting whether their savings are going to be positive and negative, and then identifying those who have significant savings capabilities, then I only need to signal potentially 35% of the consumers at each time I send them in this signal to participate. The importance of this is shown with a very simple calculation. If I utilized local marginal prices for the regions where these customers were enrolled, on average, if I enroll all these customers and just signal them without any selection, I am earning about $3 per year. If I utilize the simple selection that's able to identify those customers who have a positive reduction, which means on the aggregate I will have more kilowatt hours offered, then I am able to extract about $7 of value per year from each customer. If now I restrict myself to the top 35%, then I'm able to extract $12 per year from each customer. And just to show you that, if we do various exercises on behavioral change and gamification and so on, this was tried, your increase is only from $7 to about $8. So this shows the importance of targeting. Wisdom includes different methods for targeting. One of them is a portfolio optimization that takes response estimates and combines them while accounting for the probabilistic nature of these responses. Since these estimates have errors, we want to be able, and they vary over time, we want to be able to maximize the total response, the probability that the total response exceeds our desired target given a certain number of consumers we want to enroll. We have built very fast algorithms for this task, which are part of our library. And using this, you can obtain this type of curve here. In the x-axis, I have the target in kilowatt hours, meaning how many kilowatt hours I desire from my group, and here how many consumers I need to signal. And you can see that as I increase my target from 1 megawatt to 2 megawatts to 4 megawatts, I have to go from 0 to 6,000 consumers. Right here is the availability versus reliability curve, meaning given a set of consumers, in this case all my 6,000 guys, what is the likelihood I would meet different targets? And that is what we call reliability. And you can see here that the reliability has a sharp transition from very high reliability to near zero reliability around 3.8 megawatts. So particularly from these 6,000 consumers, we can expect about 3.8 megawatts reliably. So Wisdom allows you to do those calculations. The last thing we are doing with Wisdom is actually utilizing it to build a tool that allows us to evaluate how consumption diversity impacts values of different business models. So in electricity. So the way we do that is that we combine Wisdom data, electricity market data, different technology and policy choices, and the particular business model we want to evaluate. We process all that using optimization and machine learning under different scenarios, and then we provide the results in various summary formats dynamically. This whole process is called future casting. Here's an example of future casting. I'm taking residential consumers. I want to consider offering them a bundle of solar and storage, and their business model is going to be that once I offer this bundle, they can buy electricity at time of use prices, but sell them at the local marginal price for that particular location. Okay. So then we process the future casting and we can come up with plots like this one. Here is the benefit in dollars, or the value of this bundle for every customer, ranked according to the customer that receives the highest benefit to the lowest. And one of the things that we notice is that the first 20% of consumers, which is right here, actually enjoys benefits that are higher by 50% than the remaining consumers. This means that a company that goes into this market and is able to efficiently identify these high-value consumers will have a first mover's advantage. So where are we going from here? Today, Wisdom is available for download in our website. And what we are doing now is actually developing approaches for learning consumer preferences by more iterative approaches, so closing that feedback loop, and also incorporating more refined appliance monitoring. We are also developing future casting. Thank you.